So the title of my talk is Symmetries in Physical Laws, and I'm continuing from my first lecture. And in fact, there were some things which I'd like to go back to, so I'll just go back a little bit and let you have some of the things I wanted to say about the last lecture. So the review of the last lecture was on optimization. So we all have to optimize many things, and one of the things which I felt was not completely clear from the response of the audience was the idea of Lagrange multipliers. So I thought I will just deal with one example to tell you how it works. Let's consider that you want to maximize the function x plus y. This is f of x and y. I want to maximize this function, and I was told to write big, so I'll write it big. And subject to the constraint that g is held constant. Right? Suppose this is your problem. So let's just plot a contour plot of both these functions. So if I put x over here and y over here, the lines of x plus y equal to constant looks like this. If x plus y equal to 0, this is the line, and the line keeps on going parallel to itself like that. So these are the contour lines of x plus y, which is the contour lines of f. It also goes over here. And I want to maximize this function, and I should go as far as I can in this direction. But there's also the constraint that I want x squared plus y squared to be equal to a squared. So I'll draw a circle of radius a. So if I now look at the circle of radius a, I'm constrained to be here. So if I choose this point as my maximum, it's not a maximum because I can further increase xf without increasing g by simply going along this curve. Right? So I can keep increasing f until I come to this point where increasing f also means increasing g and violating the second condition. So this is the point which is the maximum. So this is the idea behind Lagrange multipliers. Yeah? So when you have to maximize f subject to a constraint g, you can maximize this function minus a constant times this function and get the answer. That was the Lagrange multiplier trick. I think many people knew this, but not everybody. Now, in thermodynamics, entropy is maximized for fixed energy. And the way you can do that is to minimize energy for fixed entropy. That's an equally good way of doing things. And that's how the Bose distribution is derived for blackbody radiation. Or more generally, you can just take E minus Ts, where T is a Lagrange multiplier. The temperature is a Lagrange multiplier. So just remember that. Next time you get burnt on the stove, you were burnt by a Lagrange multiplier. And say that the free energy is minimized. Now, the relation between entropy and heat is best brought about by this demo which Abhishek talked about. I'll just pass these things around. Yeah, these are exercise bands. They're made of rubber. And I've shown this to some people, but not to everybody. So you take one of them and just pull it rapidly and put it against your forehead, and you'll feel heat. And if you let it go, you'll feel it cold. So you can just pass it vertically upwards, one from here, and one from here, and one from here. So while you're doing that, I'll keep talking. So I showed you a catenoid by taking two discs and pulling them apart. There, the cross-section of that soap film was a catenary curve. And if you revolve the catenary curve, you get what you call a catenoid, which was the minimal surface. But you can also produce a catenary with soap films, by having two soap films in a wedge sort of shape. So that's what I'll show you next. We did the experiment in the lab, not this one. Yeah. So can you see here that there are two pillars here and there is a soap film connecting them. So the blue thing is the bottom thing, is the bottom face, and there's a transparent plexiglass on top of it. So instead of, if it was a straight line, the soap film should have gone from here to here in a straight line. Instead, it prefers to go to the place where the distance between the two plates is less. That's the way it chooses to minimize area. So it actually bends. And this is what you see in a mirage on a hot day. If you look at the atmosphere, which is close to the road is very hot. And the air just above the road is is rare. It's not dense at all. So when light goes from one point to the other point, it goes down and bends up again. So if you're driving on a hot day in the road, you can see mirages. You can see something which looks like water. It's actually light bending and coming towards you. So the same effect can be shown by soap films. Now, I also gave this argument that if you have, these are all optimization problems in other spheres of life. Suppose there were 3 cities at random points, and you wanted to connect them by roads using the minimum length of road. The reason for choosing a minimum length of road is that roads cost money to build, and money is always limited. So what is the shortest way in which you can connect them? You might think that I just join them by straight lines. That would be one solution, right? But that's not the best solution. The optimum method is actually to have a point somewhere in the middle here and connect all 3 by roads like that. And you can see the best, I can now tell you the argument which I didn't tell you last time. Suppose I've done this thing. I found this point to be the minimum. Then you consider a circle with this as center and this point as this line as the radius. So this is a circle. So I want to minimize, this is A, B, and C. A plus B and C. So I've drawn a circle with center C and radius C, little c. So it's clear that if I wanted to minimize the total length of the road, I should minimize A plus B plus C. But then if I look at only points which are on the circle of radius C, C is going to be a constant. So I have to minimize A plus B. How do I minimize A plus B? I just have to make sure that the angle of reflection from here is the same as the angle of incidence. So this is I and this is R. And these 2 angles have to be equal to each other. Now, if you go back to that point, you can apply the argument to A, B, or C, and you find that all these angles have to be equal to each other. That is to say, if I draw any line if I extend this line and this line, then you find that this has to be equal to that. And you can show that all the angles have to be 120 degrees. So I showed you that in the picture as well. Now, what happens when I have 4 cities? Suppose there are 4 cities here. So it's clearly not necessary to join all the cities by roads. I can do a cheap trick, and I can have 2 Y junctions here and have this kind of a configuration where all of these will have 120-degree angles. And I showed you some of these 120-degree angles. And similarly here, here, and here. Now, if these cities are very far apart, this is clearly the best way, because otherwise you're wasting a lot of length connecting these 2 cities like that. But as you bring the cities closer and closer, at some point, you'll find that if you have this situation, where the cities are disposed like this, it's no longer efficient to do it that way, but you should do it this way, where the single line is vertical and along the longer path rather than the shorter path. Right? So the optimum solution switches from this to this, depending on whether the rectangle is long or short. If it's a vertical rectangle, you should build it along the longer side. And otherwise, you should build it in each case, you should build it along the longer side. Now, what happens when you consider the optimal solution as a function of the rectangle? As you make the rectangle closer and closer to a square, suddenly the solution switches from one to the other. That is actually the germ of an idea called a phase transition in thermodynamics. And actually, you saw a version of this also in the case when I was showing you the catenoid. As I pulled the two T strainers apart, at some point, it stopped being a catenoid and became two disks. So at the lowest energy solution switches suddenly from being one to another. And that's the basis of phase transitions, the kind of thing that causes water to boil or ice to freeze. And isoperimetry is actually the idea that this was the problem that Dido faced, trying to minimize the perimeter encircling a given area or maximize the area with a given perimeter. So I'll show you a video about that. So here it is. So I should go to. Oh, it's not running, never mind. Okay, the videos are not working, never mind. So that was another video of the same effect of the. Yeah. So the other video was a video of ants. They also seem to optimize. When they want to go from A to B, they follow a particular path, which is not the. I'll just show you a photograph of it. Here's a trail of paths of ants that we found on campus while walking around. And if you follow the path, it goes through all kinds of tortuous things. For some reason, the video is not playing on this thing. Ah, you can see it. Oh, yes, it's working. So these guys are also optimizing something. They're not going in a straight line from A to B. I don't know what they're optimizing, and it's also true of the physical laws. Often we don't know what nature is optimizing, but by understanding, we can try to figure it out. This goes on and on and on, so I'll stop it here. And maybe the other video will also play from here. No, that doesn't play. All right, let's come to today's talk now. So I'm going to talk about symmetries. So the talk consists of 6 parts. In the introduction, I'll try to define what I mean by symmetry. Then talk about symmetries in plane geometry, symmetries in physical laws, and mingling of the two themes. Last time we talked about optimization. That is to express the laws of physics as variational principles rather than as differential equations. That is what I was talking about the first time. So this is basically an interplay between the two ideas, symmetries and variational principles. And finally, we'll talk about a very important theorem in physics that was developed by a famous mathematician called Emmy Noether. And finally, I'll conclude with a few disparate remarks. So take a look at this. What does it say? Yeah. So do you know the word, where the word comes from? Can you use the mic, please? Yeah, you turn it on, it'll come.
Yeah, I did.
Oh. Yeah, I think she said Arabic. Yeah. So anything which starts with an al, like many words in English which start with an al, comes from Arabic. And this is a product of the Islamic scientific blooming in the ages when Europe had gone into the Dark Ages. Many of the important discoveries of the Greeks were kept alive, and new discoveries were added by the Arab world. So it comes from a word in Arabic which means al-jabr. That means the joining together. So it was actually in the context of solving algebraic equations. So this guy invented two ideas. One was al-jabr and the other is al-muqabala. That means confrontation between. So basically, if you have an equation, if you cancel terms on opposite sides, that's al-muqabala. And if you add terms on the same side, it's called al-jabr. I know, Farah will probably tell you the meaning. Can you? Okay. Okay, now what is interesting about this is that take a look at the, okay, there is all this black stuff here which spells the word algebra, but there is some dirt here in white. Now take a look at this and compare it with this. What has happened to it? I've rotated it by 180 degrees, which you can see because the white has gone up there. Yeah? So the operation of rotating this by 180 degrees makes a result which is indistinguishable from the initial state. That is a symmetry. Right? That's the definition of a symmetry. I think you need a mic. Everyone needs a mic.
Isn't this called an ambigram?
Ambigram. It might be, but the ambi means two, right? So, yeah, right. So I think two ways if you flip it around. But there are other words for it. Let's take this word. Okay, so let me get back to that in a second. So what is a symmetry? I'm trying to define a symmetry as in terms of an object and a transformation of an object. I have something and I transform it in some way, and the transformed object is indistinguishable from the first. We say the object is symmetric if this happens under that particular transformation. So here's an example. This is called a palindrome. Able was I, here I saw Elba. Okay? If you read it backwards, it's exactly the same. Yeah? So this is called a palindrome, and that may be called an ambigram. It's a different word, right? But these are both examples of symmetries. Here it's reflection about the R in here that takes this sentence into itself, and the other one was a rotation by 180 degrees. So I'd like to have some more examples of symmetries from you. So, for example, can you give me an example of a symmetry from what I said? Let's leave the mics on, no? I think it won't hurt.
Do you mean that, should I tell a word which is a palindrome?
No, just give me a symmetry. That's to say anything which realizes the definition of a symmetry. You have to think of an object and some transformation. For example, if I take a photograph of you and reflect about this point, that would be a symmetry. Right? What?
Butterfly.
I didn't catch that.
Butterfly.
Oh, yeah. This, that's right.
Yeah.
So this is also a symmetric object.
Yeah.
Yes. Actually, this is more symmetric than we are. Really. Okay, I'll come back to that point in a moment.
Symmetric matrices. Symmetric matrices.
Yeah. You take a matrix and you basically reflect about the diagonal. And that's also, if the matrix happens to be unchanged with that operation, that's a symmetry. Yeah, what is the symmetry of a basketball? Yes, yeah. Very good, yeah. All those are examples of symmetries. So let's get now to symmetries in a mathematical sense of the term. The mathematical study of symmetry is called group theory, and you will all study it or have already studied it in your courses. If you're doing maths, you would have already studied it. In physics, you'll come across it a little later. And it's an important part of modern physics. So there are some axioms of group theory. A group is basically a set of transformations. And the set has to contain the identity transformation, which does nothing. It just leaves the object exactly as it is. And if there are two transformations, T1 and T2, if you apply T1 first and then T2, that gives you a new transformation. Both are symmetries of this system. I mean, the combination is called multiplication. So given multiplication must have the property that if you have three different transformations, T1, T2, T3, you must have three transformations. It shouldn't matter whether you multiply these two first and then the third, or this first and then the other two. We don't require that the transformations commute with each other. So that's a group. Yeah? So I don't expect you to remember this. I'm just telling you in a general way that there's a subject of group theory which studies such objects. So any questions about what I said so far? Okay, so let's go to symmetry in geometry. Now the Euclidean plane consists of points and distances between points. So for example, take the infinite plane, and the plane has got points on it. Given any 2 points, I know the distance between them. So the question is now, what are the symmetries of the Euclidean plane? What are the transformations of the plane that do not change distances? You have to map the plane onto itself in some way that doesn't change distances.
Rotations in the plane.
Rotations in the plane. Yeah, that's good. Yeah, that's a very good one. And we can think of reflections. If I take any line, any straight line on the plane, and reflect about that line, that does not change any distances. So reflections about any line in the plane is a symmetry of the plane. Now, what is nice about reflections? I'm sorry? Inversion, yeah. Inversion in what sense? That is, or you can turn the plane upside down, like back, yeah. Yeah, so so let me say, suppose I take this blackboard and I flip it like this, then I'm reflecting about some line here, right? Yeah. So if I reflect about any line, I can actually generate all symmetries of the plane. For example, if I first reflect about this line, and then I reflect about this line, this angle being theta, under reflection, the points on the line don't change at all. They stay where they are. Everything on this side comes to the other side. So all the points on the line are unchanged by the first reflection. And all the points on this line are unchanged by the second reflection. So this point, it does not move at all. So the combining 2 reflections gives me a rotation. And the rotation will take this point here to a corresponding point here with an angle theta. So a reflection about 2 lines will give me a rotation by twice that angle. So by just combining reflections, I can generate rotations, and I can get all the symmetries of the Euclidean plane. Now, how do I get translations from this? Suppose I take 2 parallel lines. I first reflect in this line, and then in this line. I'll basically translate something from here to there. So all the symmetries are generated by just reflections. That is to say, if I take reflections and compose them, I can get any translation I like and any rotation I like. So this set of all transformations that leaves the Euclidean plane invariant is called E2, the Euclidean group in 2 dimensions. Now let me go a little further. I don't want to consider the Euclidean plane, but I want to decorate it a little bit. Take the whole Euclidean plane and put a dot or a marked point. Now what is the symmetry group? So I can only consider operations that don't move this dot. Because if I reflect over here, this dot will move to some other place. And it won't be a symmetry of the Euclidean plane with a marked point. Yeah? This is mathematics, by the way. What I'm telling you is pure maths. So only those reflections about lines which pass through this point will leave it looking the same. So the Euclidean group, which had initially got translations, rotations, and reflections, now will have only reflections and rotations. And those rotations and reflections, the rotations have to be about this point, and the reflections have to be about a line passing through this point. So that reduces the symmetry group. So this is the general model of the story. Whenever you have more structure, the size of the symmetry group reduces. So this group is called the orthogonal group. That is to say, the group of matrices which are 2 by 2 matrices, which are equal, the inverses are equal to their transposes. And for example, if on the plane, I consider drawing a triangle, an equilateral triangle. What is the symmetry group of this object? The plane with a triangle. Yeah, rotation by 180 degrees across, around this point, around the center. Also reflections about these three directions. So the symmetry group is drastically reduced. So this is the basic message I want to put, that whenever you have more structure, there is less symmetry. And similarly, if I have a fivefold, if I draw a pentagon, like a regular pentagon, the symmetry group will be reduced to reflections about these things and the corresponding rotations, fivefold rotations, and so on. Now, if I take a sphere, like somebody brought up a basketball, take a sphere, reflection in any plane through the origin will leave the sphere looking the same. The distances between points won't change. Now, what is surprising is that, well, I've been talking about symmetry in the range of mathematics, in the domain of mathematics. And I told you what symmetry is and given you a number of geometrical examples. But now we want to talk about physics. It turns out that physical laws also have symmetries. And that's where physics connects with group theory. So the group of transformations which preserves physical laws is a very important idea in physics. Now, physical laws can be expressed in two different ways. Either you can write them as differential equations in terms of forces, and this is what Newton did. F equal to ma is Newton's equation. Or you can write it in integral form as an optimization principle. You can find some quantity to minimize or maximize and say delta of I is equal to 0. These two different ways of expressing the laws of physics are equivalent to each other. And each can be derived from the other. So now let's consider what happens when you ask what are the symmetries of Newton's equations. So in differential form, we solve the equations and we find a solution. So for example, if I take all the particles in the solar system and write them as RA, where A goes over all the planets and the sun, 9 planets and the sun. Maybe Pluto should be left out. Yeah? 9 planets plus the sun. And I can solve the equations and find all the trajectories as a function of time. If the laws are invariant under a certain transformation, these solutions after a transformation should also be other solutions because you're using the same laws. So for example, if I take the whole solar system and translate it by 1 light year, and I look at the evolution of the system, it should be the same. There should be no difference between where it is now and there. So Newton's laws are invariant under translations, under rotations, and also uniform motion. If you have the whole solar system moving with a uniform velocity, you cannot tell any difference. And also the reflections in space and time. Reverse the sense of time, you'll find Newton's laws to be still satisfied. Now, Maxwell's equations have all these symmetries. But in addition, Maxwell's equations also have charge conjugation. If I take all the phenomena of electromagnetism and reverse the signs of all the charges, replace the electrons by positrons, etc., Maxwell's equations, the solutions will still be valid. If I take a positive charge and keep it somewhere, I get a certain electric field. If I keep a negative charge, all the electric and magnetic fields will reverse. So this is a symmetry of Maxwell's equations, reversing the sign of the charge and electric and magnetic fields. You can see that very easily. If I take, for example, divergence of E equal to rho, 4 pi epsilon rho, I think. If I reverse here and reverse this one, the equation will still be true. So Maxwell's equations have the symmetry of charge conjugation. Now, when we write the laws in integral form, it's very easy to check if the laws are invariant. Just look to see if the action is invariant under the transformation. For example, in Newtonian physics, we would write kinetic energy minus potential energy integrated over time with fixed endpoints. It's obvious that the kinetic energy does not change under uniform motion and all it's obvious that the action does not change when you switch frames of reference. or changes by a trivial amount, yeah. And similarly, in Maxwell's equations also, you can derive them by minimizing this quantity, E squared minus B squared. If you make a change of, if you make a transformation of the kind of going to a different frame of reference, Maxwell's equations also do not, this quantity does not change. And so Maxwell's equations are also invariant. Though there's a difference between these two, these are invariant under Newtonian transformations, that is to say, x going to x minus vt. These are invariant under Einstein's transformations, that is to say, relativistic transformations. And the conflict between these two groups is what led to the special theory of relativity. You can show that if you do a transformation here using x going to x minus vt, what is inside here changes by a trivial amount. It doesn't really change in any significant way. Whereas the transformation here is the relativistic transformation of changing time as well as the spatial coordinate according to the formula which you might have studied in special relativity. Now, examples of symmetries are translations in space, translations in time, rotations in space, reflections in space, time, and uniform motion. And all these are called space-time symmetries. They're telling us about the properties of space-time, just as in the previous part, I was talking about the symmetries of the Euclidean plane. There are also internal symmetries. We already came across one of them, charge conjugation. There's also an idea called isospin. When the neutron and the proton, when the neutron was discovered, Heisenberg thought that the neutron and proton might be two states of the same particle because they are very similar in mass. He thought it might be two different states. And he introduced the idea of isospin. That is to say, isospin up is the proton and isospin down is the neutron. And he thought about rotations in isospin space. Now that is an idea that is also an internal symmetry. We can also talk about rotations in color space. I take the three quarks, up, down, strange, and I can think of rotating in this three-dimensional space. Complex rotations in three-dimensional space. Those are internal. So today we'll only talk about space-time symmetries. So finally, it is experiment that decides if a symmetry is present or not. We have to do experiments to discover if symmetries are present in nature. And for a long time, we thought that reflections in space are symmetries of nature. We already knew that rotations, translations were all symmetries of nature, but it turns out that reflections in space, it's called parity, is not a symmetry in the weak interactions. That is to say, the gravity, the strong, and electromagnetic interactions all have invariance under parity. That is to say, if you reverse the sign of, if you reflect in any plane, you get back the same laws, but it's not true of the weak interactions. But this is a very small effect. And I'm bringing up an example of a small effect. This is a face. So this is one person. This is a person. Unfortunately, they've done the lighting badly. One side is dark and the other is fair. But you can see that if you take a photograph of a face and you cut it down the middle, and you stick the two right sides together and the two left sides together, they look like different people. So our faces are almost symmetric, but not completely symmetric. And in fact, the body is also not symmetric because your heart is on the left and the liver is on the right. Yeah? Though there are some people with the opposite. I mean, there are a small number of people who have the heart on the right. I've not met any of them, but yeah. Oh, you've met somebody. Well, there's a Rise story based on this idea. And yes, there's a very famous woman scientist who did this experiment that led to the breakdown of parity. Her name is C.S. Wu. Beta decay, yes, yeah. Right? So I still want to emphasize that it's the experiment which decides whether or not parity survives. Yeah. Okay, now we come to a very important theorem, another woman who contributed to this, and that's Emmy Noether. One of the rooms here is named after her. The only room named after a woman in this campus, I think. So, unfortunately, she had a very short life. She died of cancer at a young age, relatively young age. And what she showed was that in theories where you have an optimization principle, I'm sorry? sorry, 1882. Yeah, right, you're right. This would violate something. It would violate causality. Yeah, yeah, right, right. 1882 to 1935, right. Yeah, otherwise it would look like she lived her life backwards in time, no? Yeah. So what she proved was that in theories where you have the laws in optimization form, every continuous symmetry gives us a conserved quantity. So she proved, for example, that translation in time gives us energy conservation. I mean, these are all consequences of her general theorem proves many different things, and she's got two theorems in different layers of complexity. I'm taking the simplest examples and trying to bring out the main idea. Translation in time gives us energy conservation. If you have a symmetry which is if a system is time translation invariant, you get energy conservation. And if it's space translation invariant, you get momentum conservation. So, and if it's invariant under rotations in space, you get angular momentum conservation. And you could have seen this on YouTube. There are people who'd skate on ice, and when they spin, like during the cultural program, there was one of the participants who did a Kathak dance where there was a lot of spinning around. Yeah? So ice skaters do a very similar kind of thing. And when they put out their hands, the spinning slows down. When they bring in their hands, it speeds up. That's an example of angular momentum conservation. And there's also ideas like energy conservation. Let me try to show you how that works. So this is actually a towel which I've wrapped into the shape of a whip. So I couldn't get my hands on a bullwhip, but it's actually quite common. There's a whip and people crack the whip. They start out, and the whip starts out to be pretty thick, and it gets thinner and thinner. And the kinetic energy is initially stored in the thick part. But as it goes into the thinner part, the kinetic energy is conserved, and it goes into smaller and smaller masses. And finally, the velocity, because half mv squared has to be preserved, and the mass is reducing, the velocity goes very high, and you get a breaking of the sound barrier, and you get the crack. So I'm going to see if I can do it with this. Not very loud, yeah. Nope, it's not working so well. But you can hear something, huh? Yeah. So it actually comes out a little louder than that if you do it with a bullwhip. And another idea is the conservation of momentum. This also, which I will illustrate with these two balls. First, if I drop this ball from a certain height, it has some potential energy, and it will never rise to a height above that, right? If it rises above that, I could actually use that to extract energy and run a perpetual motion machine. Similarly for this ball, right? It never gets up to the same height. But now I'm going to drop the two of them together, and this ball will hit the floor first and bounce back. And as it bounces back, there will be a collision between this ball going down and the heavy ball coming up. And because of conservation of momentum, there will be an exchange of energy between this ball, and this ball will rise to much higher heights than it started out with. So I'm going to do it so I don't break anything in this room. Yeah, I didn't break anything, yeah. So that shows momentum conservation. Now, an important idea behind Noether's theorem is that dynamical variables come in some kind of pairs. Like time and energy are related in some way, space and momentum are related in some way, and this is the same idea that comes up in Fourier transforms. When you take the Fourier transform in time, you get frequency. When you take the Fourier transform in space, you get momentum or wave vector. And the idea that there are conjugate variables is the basic idea behind quantum physics and the uncertainty principle, which came much later with Heisenberg. This was all done in 1918. very early. And in fact, she taught Einstein a thing or two about general relativity, which Einstein didn't know. Because actually, Einstein formulated his theory as in terms of differential equations, like Newton did. So he just found Einstein's equations in a differential form. But it was Hilbert who gave the variational formulation, the optimization principle. And very soon, and even Hilbert couldn't go the next step. And very soon, Noether gave the consequences of putting together symmetry with the optimization principle and showed some very deep aspects of GR, which Einstein did not realize. And neither did Hilbert. So let me just apply Noether's theorem to the very simple problem of refraction. We've already been through the variational formulation of refraction. So Noether's theorem tells you that since there's a translation symmetry, that is to say, so I have a glass slab here which goes to infinity and have a ray of light incident from here, and it reflects according to some, and it refracts. And I have some medium here with refractive index N1 and N2. So this whole situation is invariant under translations in the x direction. So Noether will tell you that there is a corresponding symmetry. And that means that the quantity, this t here is the time. The refractive index times the distance traveled is the total time. And Fermat tells you that this quantity is optimized. It's minimized in going from A to B. And according to Noether's theorem, Px should be conserved, as it will be same along the trajectory. You take it at any point, you'll get the same value. So it tells you that N1 sine theta 1 is equal to N2 sine theta 2. So the law of refraction comes out of Noether's theorem. It's probably the simplest example of Noether's theorem. So any questions before I get on to other things?
So I didn't got why it should be time. Shouldn't it be kinetic energy?
Yeah, this is the principle for light. The optimization principle for light is the Fermat's principle, which we went through in the first lecture.
So then how px equal to del t by del x? Like
Okay.
dimensionally it doesn't matches.
So let me go over the algebra here. This is dimensionally correct, right? This equation is distance times speed of light, especially, okay, I should divide this by c. Distance over speed. So let me say that this is the inverse of the speed of light. N is the inverse of the speed of light. Then it's dimensionally correct, this equation. Right? Yeah. Now, if I take dt over dx, this is equal to n times dx. Okay, no, I think I understand. If you put in an h bar, you will get it to be dimensionally correct. If you put Planck's constant, so I left out one Planck's constant, which I always do. So this is actually the wave vector. See, time and time cancel out. There's a time on the top. Let's see the cancel out. And there's also a speed of light. Okay, let me sort out the dimensions later, but I'll say, yeah, this will actually work out. Yes, yeah. Yes. Yeah. That's correct. It should be time into refractive index divided by C. That should be the time. Yeah. That's correct. Now, if I take, suppose I take X and Y as functions of X. If I take of some number S, which is not necessarily the distance, dx by ds squared plus dy over ds squared under root of all this thing to the power of half ds. This is the square root. This will be the time, because this has got the dimensions of distance. Dx squared plus dy squared under root has got the dimension of distance. So this is dimensionally correct. Now if I take dt over dx dot, what I'll find it is n over c times this whole bracket squared times twice dx over ds. So the dimension of this is 1 upon velocity. I mean, n upon, this is the velocity. And then there's also, the 2 is also cancelled out. Dx over ds. So this is distance over time. I'm missing some. And this is a distance also. Yeah. Yeah. So I think that is it. Okay. So I'm taking, let me take this S to have any dimension. It seems to cancel out. Okay. So let me, in fact, assume it to be dimensionless. Then dt over dx dot is got the dimensions of n over c times dx over ds times this thing to the power of half, which is got the dimensions of t upon d squared, because there is a speed of light here, which is distance over time, and there's one more distance from here. So it's d squared times dx over ds. So if I put the whole thing together, d over t is equal to the speed of light, let's say, times n, and then there is wait, I'm getting something wrong now. No, so I can take S to have the dimensions of distance, but that shouldn't change anything. I think that the net the net dimension is going to work out to be 1 upon x, I think. So it should be the dimension of wave vector. And I think that is true, because there are, yeah. Okay, let me sort this out properly later, yeah? I'll just carry on with it. But see, the thing is that normally this thing which comes here has the dimensions of energy. The Lagrangian usually has the dimensions of energy. Here I'm using something which has got the dimensions of time, yeah? So yeah, I would have to put in some constants to make it into that. But I use this one because it's the simplest place where you could see a variational principle and know this theorem at the same time. So forgetting about dimensions, this is correct, but I'll sort out the dimensions by the end of the talk, I think, in the question session. Okay. So any other questions? Okay, now I'm going to wind up with the idea, and we'll have questions after that. Let's put together all the ideas we've had so far. So I told you that whenever you have more structure, we have less symmetry. So this has led to an evolution of our ideas of space and time. So throughout history, we'll find that space-time has lost structure, and as a result, it has gained symmetry. That's the story I'm going to tell you. So we have had several ideas about space and time. First, going back to Aristotle, then improved by Galileo, further improved by Minkowski, and finally Einstein's general theory of relativity. They're all different ideas about space and time. And they have progressively, this has got more structure, slightly less structure, the same amount of structure but slightly different structure here, and finally even less structure. And consequently, the symmetry is, here it's very large, gets a little smaller, it gets different when you go from Galilei to Minkowski, and finally it gets huge when it gets to Einstein. The amount of symmetry in the physical laws. Yeah.
So what do you mean by structure? What do you mean by structure in this context?
Yeah, I'll tell you what I mean by structure in the next slide. So here is what I mean by structure. I'll start by telling you what Aristotle thought about space and time. So he thought of space, and this is a space-time diagram. I've plotted x along the x-axis, and I plotted time along the t-axis, right? So this is the structure with Aristotle imposed on space and time. He thought of a notion of now, that all the points in space-time which are happening at the same time are called now. And now is the same for everybody. There's an additional notion which he had, which is the notion of here. All the points, all the events that happen at the same location, that place at different times. So for example, the Battle of Marathon happened in a particular place in Greece at a certain time. That might have been over here. And 200 years later, there might have been, some other event here where at the same point. So he thinks of space as being characterized by two ideas. One is here, and the other is now. Yeah? This is Aristotelian space-time. Anushka, you don't look happy with what I'm saying? You disagree or you agree? Okay. And in addition to this, he had the laws of motion, which tell you that the force is proportional to the velocity. If you apply a force, something will move with a certain velocity, which is related to the force. And if you remove the force, it will slowly come to rest. So rest is the natural state of objects in Aristotelian spacetime. Any object, if it's left undisturbed, it will come to rest. And it's actually a pretty good approximation of spacetime. Like, if I don't do anything, at some point it comes to rest. It's even more true that if you go to a viscous fluid, the kind of fluid which an amoeba moves in, this fluid itself can be thought of as space-time, and everything comes to rest in the rest frame of the fluid. So the rest is the natural state, and the space can be thought of as a kind of fluid in which everything comes to rest. So this is Aristotle's idea, and it's actually not a bad description of a very viscous fluid. An amoeba would be happy to subscribe to Aristotelian dynamics. But it's certainly not true in our world. If you hit a cricket ball, for example, it doesn't come to rest. It takes a long time to come to rest. Now, with Galileo's space-time, Galileo had the notion of now, that all points which are at the same time. The notion of simultaneity was the same for everybody. So this is built into space-time, the notion of now. But the notion of here has disappeared from the universe, from Galileo's universe. So let me give you an example. Suppose you're on a train going from Bangalore to Chennai. So if I ask you, where did you have breakfast? If you were sitting on the train, yeah, you would say that I had breakfast in, let's say, someplace in between. I don't remember the stations. Okay, let's say somewhere in between Bangalore and Madras. I had my breakfast in that place. But if you're, if you're sitting in the train, if you're sitting on the ground, you will say that, let's say, suppose Anushka was going from Bangalore to Madras and passing through city, which let's say there's a place called Kamasamudram on the way from Madras to Bangalore. Okay. And Farah was on the platform and Anushka was in the train. So if I ask Farah, where did Anushka have a breakfast? She will say she had a breakfast in Kamasamudram. Whereas Anushka will say, I had my breakfast in compartment B12, seat number 6. She's in the moving frame of reference, and she will have a different notion of where she had her breakfast. So the notion of here as an absolute notion has disappeared. Yeah? So some structure has gone out. The vertical lines which were here have gone out. So symmetry is reduced, and I hope this answers your question. I mean, the structure has reduced, and the symmetry has improved. Now, the uniform motion, the natural state is not the state of rest, because there's no preferred state of rest. All states of uniform motion are equally good. So uniform motion has become the natural state. And this is characterized by Newtonian dynamics. And these equations are invariant when you go to a moving frame of reference. So symmetry has now increased from Aristotelian symmetry to Galilean symmetry. So I hope this is clear, that we have actually had an improvement in our ideas of space and time. Yeah.
How does taking off the notion of here convert velocity in that equation to acceleration?
How are we?
How does removing the notion of here convert velocity in Aristotelian dynamics to acceleration here?
Yeah. See, velocity is not invariant under changes of frame. If I go to a different frame, the velocity changes, but the acceleration stays the same. This guy stays the same. Because acceleration is dv by dt. If I had a constant velocity a, v plus a, and take its derivative, the a derivative drops out. Yeah? So acceleration is invariant under changes of frame, while velocity is not, provided it's uniform acceleration. Now, when we got to Minkowski, what we forget about is both here and now. The notion of simultaneity is not there. That is, we don't have any horizontal lines which characterize now, and we don't have any vertical lines which characterize here. Everything has gone out the window. The only thing that matters is here and now, which is a point here. An event makes sense. But notion of here and now don't separately make sense, only here and now. And here and now together means a particular point in space-time, which is an event. Another thing which makes sense to everybody is the path of light rays. So light rays go like this. And you notice I was previously plotting t here. Now I've plotted ct. C times t makes time and space have the same dimensions. I measure space in seconds and I measure time in seconds. Everything is measured in seconds. And then I have this notion of light rays, which are the only structure in space-time. And the Minkowskian transformation has a symmetry between space and time, thinking of uniform motion as achieved by a rotation that takes time and space and mixes them up. So it's a rotation through an imaginary angle, takes time and space together. So if I were to just write this in equations, an ordinary rotation has the property that xy prime is equal to cos theta, sine theta, sine theta, cos theta. This is in terms of 2 by 2 matrices times x and y. Whereas in Einstein's theory, t prime and x prime is equal to cos alpha, sine alpha, sine alpha, cos alpha times t and x. So this transformation takes x squared plus y squared and keeps it invariant. This is, of course, the distance between the two events. This transformation takes c squared t squared, c squared t squared minus x squared, and keeps that thing invariant. So it preserves the speed of light. So the diagonal 45-degree lines I've drawn are the speed of light, and light is going outwards and inwards. And those lines don't change, no matter which frame of reference you're in. So the amount of symmetry here is the same in the sense that uniform motion is a symmetry here as well as in Galilei transformations. But what has changed is that the group is different. The multiplication law for how you add velocities is different. That's the only difference between Einstein and Galileo. Finally, when you come to Einstein, he throws everything out of the window. What he says is that in the presence of gravity, curved spacetime captures gravity, and the natural state of an object, which is not acted on by forces, is geodesics, the shortest paths in that space. So this has got much less structure and much more symmetry. It's not just uniform motion, which causes the laws of physics to be the same. An arbitrary amount of motion is also possible. You don't have to have a uniform acceleration. You can have, uniform velocity. You can have any acceleration, and it's still a symmetry of the theory. And this results in a huge symmetry group, and symmetry group is the size of the symmetry group is so huge that in some ways it becomes a handicap. This theorem tells you some things about that symmetry group, which makes it very hard to quantize this theory because there's nothing you can hold on to. That's one of the outstanding problems of today, applying quantum mechanics to gravitation. Actually, I should also clarify that Noether had two theorems. One theorem I already mentioned. The other theorem is too hard for me to put across at this level, but it's a second theorem that tells you that the excess symmetries of Einstein's theory will present some problems to applying quantum mechanics to it. Okay. So let me now, I'll just maybe, yes. Yeah, so I talked about this connecting 4 cities by road. Suppose I have 4 cities by road like this. I told you that the minimum solution is to take this path along the longer diagonal. Right? But what if I told you that this was a square? Then which would you choose? They're both equally good. You can either do it this way, or you could take the same square and do it this way with 120-degree joints everywhere. I'm not drawing it as 120, but these are all supposed to be 120-degree joints. So this solution and this solution have the same energy. Yeah? So it can happen that when you optimize, you get solutions which don't have the symmetry of the problem. The symmetry of the problem was that if I take a square and rotate it by 90 degrees, it looks the same. But the solution does not look the same. So in a problem where the any problem where you have an energy which is being minimized, the lowest energy state is called the ground state in classical mechanics, or it's also called the vacuum sometimes in quantum mechanics. The lowest energy state has no particles, so you call it the vacuum. It can happen that the energy is a symmetric function, but it can also happen that the ground state may not have the symmetry of the energy. This is called symmetry breaking, and at low energies, you will not see the symmetry. But when you get to higher energies, you can see the symmetry of the action again. You can find the laws are symmetric. But if you're stuck in a state where the ground state is not symmetric, you may think that the symmetry is not present. And this is the basis of the Higgs mechanism, superconductors, and a kind of symmetry called gauge symmetries. They're all broken in this manner. Examples of this, let me give you 2 examples. One is magnetism. Magnetism is a set of spins which interact with each other according to an energy rule. If they're parallel, they have lower energies, and if they are anti-parallel, they have higher energies. So if you put a bunch of magnets together, the whole Hamiltonian, the interaction energy is invariant if you turn the whole thing. But below a certain temperature, you find that the 2 spins like to align in an arbitrarily chosen direction. They might all point in one direction or some other direction. That direction is chosen in a way, and that the fact that it has magnetization, spontaneous magnetization, tells you that the ground state is not invariant under rotations. When you turn a magnet around, you're changing the ground state. It doesn't look the same. And if you lived in a place where the magnetism was all pointing in a certain direction, you will think that the space is not isotropic. So that's an example of symmetry breaking. And of course, I mentioned that parity is broken in the weak interactions. So symmetries come and go depending on the energy scale. So this is the video in which, yeah, let me see if this one works. Yeah, so this is a video in which I've done this same experiment with the soap film. Oh, it got, okay. You can see that the soap film chooses the solution. This is actually supposed to be a square. It's just been taken from an angle, so it looks like it's not a square. And the solution actually breaks the fourfold symmetry of the problem. So finally, I'll just close with, maybe I can skip this. I can come back to this depending on whether there are questions. Maybe I'll stop for questions, and if there is no questions, I'll take up this again. Yeah.
What does nature prefer, symmetry or structure?
What is?
Nature prefer more, symmetry or structure?
What is greater?
What does nature prefer?
Yeah, actually, see, the structure determines the symmetry. So the structure is there in space and time, which we discover from experiments. So for example, when we grew up in a universe where all the velocities were small compared to the velocity of light, we thought there was a certain amount of structure. We detected a certain structure. Then we used the symmetries that that structure had in order to develop our ideas about dynamics. So they're closely related. Structure determines the symmetry. And conversely also, if I have a symmetry, I can ask, what is the structure that this symmetry leaves invariant? Both are equivalent points of view. So in effect, it's a point of view that was taken by Felix Klein. He classified geometries according to what is the symmetry of that geometry. So Supurna talked about projective geometry. That has got a different symmetry group compared to Euclidean plane geometry. Yeah. A mic? There. There's a mic up there.
Sir, could you explain physical symmetry again?
Physical symmetry?
Yeah.
So I have a physical law, like say Newton's equations. It tells me that a body moves uniformly, or stays at rest, or moves uniformly. Now I ask, what are the transformations I can make that leave the stuff looking the same? That the laws are respected in one frame, they're respected in all frames, right? So I know that if I move a little bit, right, if I translate myself, this law will stay the same. Because x will go to, let me do this explicitly. If I take d2x over dt squared equal to 0, this is Newton's law, first law, when there's no forces. Yeah. So if I take x to x plus a, where a is a constant, if it is true in this frame, it will also be true in this frame. And similarly, if I take x to x plus vt, if it's true in this frame, it will also be true in this frame. Because when I differentiate twice, this goes away. So like that, I can discover what are the transformations that keep this law looking the same. In addition, I can find, if I take t to minus t, that will also work. Right? And so on. So that, right?
We can take different perspectives and see whether it stays the same or not.
That's right. So for how many people are these laws true? For example, if I go to an accelerating frame and an object is at rest, I will think that that object is accelerating. Yeah. Right? Even though there are no forces acting on it. Yeah. So in Einstein's theory, that is also an allowed transformation. So I will say that that object is falling under the influence of gravity because it's accelerating.
Yes.
Yeah. Okay, now let me just finish up this. So I've been telling you, remember we started out with a very philosophical discussion about Leibniz versus Voltaire. Leibniz was claiming this was the best of all possible worlds, and it looked like there was a philosophical discussion. But suddenly that led into some very physical ideas based upon the fact that the laws of physics do permit an optimization formulation. It looks like all the fundamental laws of physics can be written in an optimization form. So if you're talking about maximum or minimum, like a system tries to maximize entropy, and it can also minimize some other quantity. It might minimize the action, but maximum and minimum can be converted into each other by just reversing the sign of the object. So that's not a big deal. Yeah? But I want to give you some examples where it's neither a maximum nor a minimum, but it's an extremum. Yeah? So I've told you that Fermat's principle tells you that light takes the path of minimum time. Now I'm going to contradict myself and say it's not always true. So let me give you an example. Suppose I have a lens over here like that. I can find a point here. I don't remember my optics well enough to say where it focuses, but I can get it to focus at some point. So I have a point here and a point here. Right? So you agree that I can do this? I can put a source of light here and get the light to pass through the lens and focus at this point. So this is the object and this is the image. Right? So up till now, no problem. But let me ask, what happens if I want to consider a ray of light that goes from A to B here? Now you'll tell me that this is the path of least time, this is the path of least time, and this is the path of least time. So it will get from here to there along this path. So now I'm asking, is this path from A to B a minimum or not? Yeah. Is it actually a principle of least time? The answer is no, because I can go along this path like this. See, these two paths have equal times, right? The time to go from A to I along this path is the same as the time to go along this path. But now what I do is I go along this path like this, do all the right reflections, and when I come here, at the focal point, I go like that. Now this is clearly not a path of least time because I can reduce the time by taking a shortcut here. Yeah? So it's actually a path of stationary time. That is to say, the time taken to go from here to there is actually stationary, but it's not a minimum because I've shown you that I can reduce the time taken by going along the other path and then slightly shortening it. So the variational principles of physics are not always extremum principles. I mean, they're not always maximum or minimum principles, but they can sometimes be extremum principles. That is to say, there's a saddle point. But that only happens when you have widely separated events. So for example, if I take any small piece, it's still a minimum. Any small piece of this is still a minimum between its endpoints. But when you take larger parts, you find it can sometimes be a saddle point rather than a maximum or a minimum. A good example of this is the sphere. So let me take a sphere and look at the shortest distance between the North Pole and some point here. It's clearly the shortest distance like this. But if I keep going like this, at some point, there will be multiple paths connecting the North Pole with the South Pole. After that, it's no longer the shortest path. Because if I go around all the way around and come on the other side, it's actually it's a pretty long path. Not the longest path, but it's a long path. It can be shortened by just coming off the South Pole. Taking a shorter path will get you from here to there. So it's not always a maximum principle or a minimum principle, but in some cases it can be an extremum principle. Another example is if I take 2 points like this and a mirror. This is the first thing I started out with. I showed you that the least time path comes like this, where this angle is equal to this angle. This I did in the first lecture. Now suppose I were to bend this away like that, it would be even more true that it's actually the least time, because these paths have greater time. They have to go much longer distances. But I can do the opposite thing and bend it this way. Then the other parts will start becoming also shorter in time. If I take these 2 points as the focus of an ellipse and draw an ellipse like this, all the parts have exactly the same time, right? But if I take a point here and bend it, give it more curvature than an ellipse has, it will actually be an extremum and not a maximum, not a minimum. So these are counterexamples to the idea there is always a maximum or a minimum. It's always a saddle point, at least. Only the first variation of the action has to vanish. The second variation can be either positive or negative, and that has been brought up before. Now, this was a rather fine point. You shouldn't worry about it too much, because whenever the two ends come together, you always find it's a minimum, or you can make it into a minimum. Now, Leibniz told us that we live in the best of all possible worlds, and Voltaire, of course, disagreed with him. But at the end of his book, Candide, he comes up with a more positive message, saying the world is not such a great place, but you can't change that. The best you can do is to cultivate your own little garden. That is to say, you pick up something that you're passionately interested in, and you work on that. Don't try to worry about what's going on in Ukraine or Israel or any other place. You just try to focus on what you can do with your time and your talents. And you grow your own garden means you cultivate your own mind, metaphorically. So with that message, I'll stop.